Hello, this is Mrs. Scarple, and in this video I'm going to review Lesson 3 from Unit 1. In this lesson we compared an exponential function to its inverse. The premise of our context was the story of the tortoise and the hare. The hare had given the tortoise a 1-meter lead or head start in the race. And the function for the tortoise's speed, or distance I should say, was d of t equals 2 to the t power. So its distance covered in any amount of time was always 2 times more than the previous second. So time was in seconds, distance is in meters. So when the race began, the tortoise started at 1 meter. And we can calculate that by substituting 0 in for t, and 2 to the 0 power is 1. I can do the same thing at 1 meter. 2 to the 1 is 2. At 2 meters, 2 to the second is 4. 2 to the 5 is 32. 2 to the 6th is 64. And 2 to the 10th, I'm just going to double check with my calculator here. 2 to the 10th is 1024. So we can plot this on our graph. So we have times of 0 through 10. So it's 0, 1, 2, 3, 4, 5, 6, 7. Oops, I can't spread it out that far. I don't have enough spaces or lines on my graph. So let's just start, let's renumber, and I'll do every other one is an even number. 0, 2, 4, 6, 8, and 10. And I'm going to go by hundreds, so I'm going to label every 200 till I get, oops, so that should be 600. I almost doubled it. 600, 800, 1,000. And we know that at 0 seconds we were at 1. At 2 seconds we weren't much higher. 5 seconds was at 32, so a little bit higher. Oops, I need to make sure I'm at 5 seconds here. 5 seconds was at 32. 6 seconds was at 64. 10 seconds takes us clear up to the 1024. So we can see, if I look at the 4 points that I have here, we have a very slow increase, and then it quickly increases. We call this an exponential function. Another way I could tell you that this is an exponential function is that my unknown is the exponent. In terms of the tortoise and the hare and their race, the domain, because this is time in seconds, we can't have negative time, so we know that the domain has to start at 0, but we don't know how long. This could go on forever, so our domain goes off to infinity. And our range starts at 1 and continues on to infinity because we are always increasing. Our y-intercept is at 0, 1. So instead of starting at 0, 0, an exponential is going to start at some value larger than 0 most of the time. So 0, 1, if we had a multiplier in front of this, it would be higher than that. So this is our initial function. Now, you haven't been introduced to how to undo an exponential function yet. So what we're going to do is we're just going to do our table backwards here. Because we have learned from our linear functions and our quadratic functions that the table, our inputs and outputs switch. I'm going to change my numbering so that my time is now my output. And just like I did before, I'm going to label every 2, but on each line. And I'm going to go by hundreds, but label every 200 for my distance. So this time the input is distance and the output is time. So at 1, we are at 0, so really close to that origin. And at 32, we are going to be at 5. At 10, well, at 6, we're at 64. At 10, we're at 1,000, or when we're at 1,024, we're up here at 10. So I've switched my axes, which has changed. My graph is still increasing, but it's a different kind of curve. It starts increasing quickly and then starts to slow down on my increase. And I did not do a good job of graphing these points. Oops, that's not what I wanted. Here we go. So let me go from the other way, see if I can do it a little bit better. There we go. Now we have the idea. So this is our graph of our inverse. The domain is starting at 1 this time and going off to infinity. So it's the range of our function is now the domain of our inverse. And then we have our range starts at 0 this time and increases to infinity. And this time we don't have a y-intercept. What we do have is an x-intercept. At 1, 0. So switching the input and output of our y-intercept from our function gives us the x-intercept of our inverse. Now, if I were to graph this for the domain for all real numbers, and I'm just going to use a scale of 1 here. So 2 to the 0 would be 1, 2 to the 1 is 2, 2 to the 3 is 8, or wait, 2 to the 2 is 4, then we have 2 to the 3 is 8, 2 to the negative 1, when I say domain for all real numbers, that means I can use these other values, and it's going to get closer and closer to 0, but never actually equal 0. So this is the domain of that function for all real numbers. Now its inverse I'll do in red. So instead of 0, 1, we'll be at 1, 0. Instead of 1, 2, we'll be at 2, 1. Instead of 2, 4, we'll be at 4, 2. Instead of 3, 8, we'll be at 8, 3. Instead of negative 1, 1/2, we'll be at 1/2, negative 1. And we'll see that these values get closer and closer to the y-axis without actually ever equaling an x value of 0. So if we look at these, I can see that without any domain restrictions, the inverse of an exponential is going to be a function. So that means all of your exponential functions are going to be invertible. We can also see from this graph, I'm going to draw it in blue here, that the inverse is reflected across the line y equals x, just like our linear inverses and our quadratic inverses. So all of our inverses, when we graph them, will reflect across the line y equals x. And we can say that any exponential function is going to be invertible, so you don't have to restrict the domain on any exponential function. So takeaways, this is some new terminology for you. I hadn't named this yet up to this point. The inverse of an exponential function is what we call a logarithmic function. I'll talk about how we write that more when we get into Unit 3, or excuse me, Unit 2, when we actually start working with logarithms. But for now, you just need to know that the inverse of an exponential function is a logarithmic function. You don't have to worry about undoing the equation to write the logarithmic function just yet. As far as graphing goes, or the table, you just switch your x and y values, switch your inputs and outputs. Both exponential and logarithmic functions can have different bases. We happen to look at an exponential function that had a base of 2, so its inverse is going to be said to be a logarithm of base 2. So the base of your exponential and the base of your log are going to match, but these bases can change. I could say if I had f of x, actually let's change it to a different function name. If I have g of x equals 3 to the x, then the inverse of g of x will be log base 3 of x. So the bases will be the same between an exponential and its inverse, but we can have different bases is what the statement there is saying. And this concludes the review of Lesson 3 from Unit 1.